5 Wednesday seminars we'll have this summer in the workshop. As I've said to some of you before, the goal of these seminars is to actually introduce you to something perhaps a little bit outside of your main area of research, but which is nonetheless very interesting and exciting, and hopefully you'll learn something new which you can maybe use in your research. So in the first of these 5 seminars, I'm happy to introduce our speaker today, Professor James E. West. Many of you in this room know him as the inventor of the electric microphone, which is the technology used in, I think, more than 90% of the microphones being produced today, telephones, tape recorders, and so on. He started his academic career in Temple University, where he studied physics. Then he went on to Bell Labs, where in, I think, '62, he and one of his colleagues invented the electric microphone. But since then, he has gone on, done many interesting things, and he has more than a couple of hundred patents to his name. He has been recognized for his achievements and elected to the National Academy of Engineering and inducted into the National Inventors Hall of Fame. He's a fellow of the IEEE, past president of the Acoustical Society of America. He was awarded the first Golden Torch Award by the National Society of Black Engineers. I could go on, but I think I should let him talk. So I'll stop here. But I'll just say that last fall we were very happy to find out that he is coming to Johns Hopkins University, where he's now a research professor in the Department of Electrical and Computer Engineering. And he's going to talk about something that is a more recent passion of his, microphone arrays and their application.
Thank you very much. Good morning. I thought I had this talk all figured out last night, but it's changed, and I'm not sure which iteration you'll get, but please feel free to ask questions along the way if they come up. What I'm going to talk about this morning are essentially microphones, directional microphones. And I'll also talk about some of the applications of those directional microphones, especially with regard to speech recognition and being able to just being able to communicate. It's no mystery why the telephone came about as it did, namely with the microphone right at the lip, right? And the microphone is there because the problem in picking up from the human to machine interface is to get as clean a signal as you possibly can. Okay. Now, for many applications, to have to hold a handpiece or to have a microphone right in front of your mouth is inconvenient. And so many of us for many years have been trying to increase the distance between the human and the microphone without degrading the signal. And we've done this primarily using directional microphones, which I'll talk a lot about. And then the next step is to combine directional microphones with signal processing to even further improve the signal to noise. I recently attended a conference on microphone arrays in Europe. And one of the astounding things is that one of the future cars, the Mercedes, I don't remember the model number, but already has 9 microphones in the car, right? They have a short array across the rear view mirror for the driver. And because these cars are so big, in order to communicate with people in the back seat, there are microphones in the back seat so that they can communicate with the people in the front seat, okay? Now this may sound absurd and seem absurd, but my colleague Gerhard Sessler says that every car, and he didn't put a time limit on this, will have at least 20 microphones in it. And when you stop and look at today and the fact that already we're up to half that number, and we haven't included surveillance and auto theft in the acoustic regime, which I think is also very possible. So it's really easy to see how microphones can get that, or that many microphones can get in the car. If I hit the right button, I have to hit another one so I can see what I'm doing too. Many of you have seen this, the wheel of the science of acoustics. I'll talk a little bit about about transducers, which happen almost in the center of the circle, but mainly about speech, about communications, and about psychological acoustics. Condenser microphones have been around for some time. They were invented by E.C. Wente at Bell Labs in 1917. Now, so far, condenser microphones are the most linear transducer that has been that's around. Okay, this means that there is a direct proportionality between the pressure that impinges on the diaphragm and the voltage that you get out. Now, condenser microphones have one major drawback, and that is that it needed a battery of about 200 to 300 volts in order to get this device in a linear fashion. Let me see if I can explain how it works. If a sound pressure impinges on the diaphragm, the capacitance in this gap between the diaphragm and the back electrode changes. So you get a change in capacitance. And what you really want is a change in voltage that's proportional to the change in capacitance. And in order to do that, you need a battery to be able to draw some charging current through this resistor. As the capacitance changes, you get a small current through this resistor, and therefore you can see a voltage change that's proportional to the capacitance. Now, I'm going to go back in time because to just bring you up on what Sessler and I did. Piezoelectricity in ceramics, and this is lead zirconate titanate, PZT, and this is a very brittle material. And in the non-polarized state, the molecules are basically random. When you elevate the temperature of the material and place it in a strong DC electrical field, you can align these molecules in the way that I've shown over here. Now, if you electrically stress that material or mechanically stress that material, you get a response that is nearly proportional, depending on the magnitude and the conditions, namely what this material matches, the rho C of this material. And as I said, it's very brittle, so it doesn't match air very well. And so the transfer in both directions is a little weak. And so what is generally done is that you take a little small piece of this material and you put it on a metal plate, right? And now this thing becomes like a tennis racket. If you deflect that plate, the piezo material will bend and you'll get an electrical signal out. This phenomena in materials was discovered by Madame Curie in about 1868. She and her husband, P. Curie. This was mainly in radium that was found out to be piezoelectric. Much later, in about 1968 or so, Fukada and Furukawa found that they could take PVDF, polyvalidine fluoride, and that there's a strong dipole moment between the CFF bonds in this material. And this material, again, is random, but you heat it and again apply a strong electrical field. What you get are the molecules all line up, and now you have a very strong piezoelectric effect in this material. And they were able to make transducers out of that material. By the way, electret microphones have been around for a long time. I guess the first one was also in about 1928. But both the PVDF and the organic wax electrets, these were made out of Canuva wax and and a bunch of other waxes that they mix together and polarize. It's a very, very interesting story that I like to tell sometimes. Back in the 17th century, Sir Francis Gray took molten wax and allowed it to solidify in an iron ladle, right?
Wow.
And
I didn't hear the last word.
an iron ladle, just a iron dish, okay? And once the wax had solidified, he dumped it out of the ladle, and in some way for which we don't understand a lot about these materials, the material was electrified, okay? And the way he knew this was that he hung a pith ball over this molten wax. And this is all in England, and on dry days, the pith ball would swing very high. When the humidity came in, the pith ball would come down. Well, ironically, he discovered the one property of electrets that had been a tremendous problem until Sessler and I, and that was that water molecules can compensate the charge in these materials. And in fact, that's one of the problems with PVDF. Humidity and high temperature, the Curie temperature of this material is only at about 80 degrees C of pure PVDF. And so if the transducer reaches close to that temperature, it begins to depole. So the situation is very unstable. What Sessler and I did was to use Teflon, okay? Now, there are two things about Teflon that are different from everything that was done before. One, it's an amorphous material, and there is no dipole moment in the material. And while there are many theories as to what really happens in these long chain molecules, one is that when you expose these materials to very large electrical fields, you can break the bonds between the CFF molecule. And once you do that, you attach a radical and a real charge to that material, the radical being here and the real charge here. Now, what we can do is that we can get charge densities up to about 10 to the -7 coulombs per centimeter square, I believe, right? And what that means is that, under certain conditions, you can generate a field that is comparable to 200-300 volts, okay? It's just like charging the plates of a capacitor to 200-300 volts. You get the field in between that. And we can do that. And this is very permanent. In fact, you destroy the material before you dump the charge out of the material. And so what Teflon allowed us to do was to greatly simplify the condenser microphone, because now you can make the diaphragm out of Teflon. This is about 25 microns thick, about 1 mil with a metal coat on one side, and we implant the charges in the material, right? And now you get a field in the gap and a field in the material. And now if you distort the capacitance, you get a voltage over here that is proportional to a change in capacitance, which is precisely what you want, okay? Condenser microphones still today, standard condenser microphones sell for about $1,000 and up, and you can buy Electret microphones for 10 cents a piece. So now you have a very linear device that's in all telephones and just about everything else that has a microphone. They can be made in various sizes. We've made them up to, I don't know, about 10 inches across, and I just received the other day Electret microphones that are 2 millimeters by 2 millimeters, okay? And these were not even MEMS, Okay, MEMS microphones can even be made smaller than that. What I'm going to do now is to talk just in general about directional microphones, because as I said before, what we'd like to do is to move that microphone away and get the same quality that you get if the microphone were right in your mouth, right? And one way to do that up front is to make the microphone directional, okay? And one of the properties that I'll talk about from here on is the directivity index. And simply, the directivity index is that if I had an isotropic sound field, which you never do, but you know, you have to pin your hat on something, and I have a omnidirectional microphone in that isotropic sound field, and I have a microphone with certain directional characteristics, right? The directivity index is the ratio of the omnidirectional microphone over this directional microphone, and we express that in decibels. So if I have two pressure sensors, two omnidirectional microphones, and I subtract those two sensors, and if I let the delay tau equal 0, what I get is basically a figure 8 characteristic, and that's very easy to see. And that is for sound pressure coming in from either the front or back. These microphones are spaced by some distance, so the arrival time is going to be different at the two microphones, and so you get a finite output in these two directions. Because they're on the same plane, for a sound wave coming in from the top or from the bottom, you get 0 for a perfect dipole. This gives you a directivity index of 4.8 dB. This microphone for distance is not too practical unless you have people that are sitting across from each other. So what many have done is to make the infamous cardioid microphone, okay? And the cardioid microphone has you make this delay equal d over c, where c is the speed of sound, okay? And this is done essentially mechanically. What they do is they've learned to treat certain cloth materials to give the right resistance that they put on the back cavity of the microphone, which now sets the d over c to the right value to give you a cardioid, which gives you a directivity factor of 4.8 dB. What is more interesting is to make tau less than d over c, and you see what you gain here is a few dB in terms of the directivity index, and this is very, very practical because it narrows the front beam. This means that I have to aim it more carefully, but at least I'm picking up less of the ambient noise that may be surrounding the microphone. Nobody makes these commercially, right? And so what we've done is to take a cardioid and physically change the, this should have been next. I'm going to talk a little bit about communications too, but I tell you, let me go to the next one and then, whoops, I didn't put that in. I thought I had put that in. Anyway, since it's not there, I probably didn't save after I did the last iteration. What happened, the way we achieved this is we took the microphone, the cardioid microphone, and put it in a rubber boot, right? And we positioned this rubber boot had two openings to admit sound, one for the front and one for the back of the microphone. And we positioned the diaphragm in such a way that we got the right delay to give you a hypercardioid. Now this microphone has been is in one of the new Avaya telephones. Here are the two ports right here, this hole here and this hole here, for the microphone. This is an ISDN, not an ISDN, this is an Internet Protocol telephone. And I'll talk a little bit more about later on why that's important and in terms of extended bandwidth and so forth for communications, which is also interesting, I think, from the standpoint of speech recognition and so forth. began to look a few years ago at applications of the microphone for speech recognition. And we chose the car as an environment to work in, mainly because it's a rather confined space and it's very noisy. So, we gain on one end, we lose on the other. And what I'm going to describe are some results in which we went out and recorded car noise, okay? And then we came back into the lab and we made a cube, right, with loudspeakers, with these 6 loudspeakers facing from every direction, right? Now, we also put a delay, a different delay in each loudspeaker, and this is to make sure that you don't have hot spots in that regime, right? And so we made sure that as it is in a car, the sound is pretty uniform throughout the car, right? That we wanted the same thing in our test cube, and we achieved that with 6 loudspeakers surrounding this. Now, also, in doing speech recognition, especially when you're playing around with the signal-to-noise ratio, you can't use a human being. You can't use a human being because a human being is not reproducible. So what we did was to record the speech, use the B&K artificial mouth to generate the sound, right? And at that time, we were also interested in echo cancellation from the standpoint of two-way communications, because that's the only way it would work. So we had a echo canceller. I'll talk a little bit about echo cancelers later. And then in automatic speech recognition system. And then here, this is a signal-to-noise ratio here versus the percentage correct of the speech utterances. And these utterances were, call, please call. It's a limited vocabulary, but it's the sort of thing that you would do to dial people hands-free in a car, right? And what I have here are omnidirectional microphones, which is the recognition accuracy here versus the microphone that I just described, the hypercardioid. Okay. Now, mind you, that there's a maximum of 6 dB improvement that one expects. And this is one of the things in the data that we don't understand. It's the reason it's not published, and the reason that I bring it up here is somebody may be able to explain it, okay? What you would expect, and you get exactly what is predicted, and that is if the signal-to-noise ratio is much worse than 15 dB, ASR goes away. You just can't do anything with a signal-to-noise ratio that is not greater than 15 dB. And sure enough, we see a knee here in both the omnidirectional microphone and the directional microphone. Now, the interesting thing is that if I come down here 6 dB, which will put me at this point, I should be falling off at the same rate as the omnidirectional microphone, but I'm not, okay? I'm going out even further to get a signal-to-noise ratio of 5 dB, 80% correct, right? Now, that's, of course, not good enough, but the real question is, why doesn't this behave as an omnidirectional sensor? Now, okay, so that's one set of data. Go to a second set of data, and things even improve a little bit. One of the other things that we did was to try some noise reduction schemes, okay, on top of the directional microphone. Now, there are 2 things that happen here. You notice there's a limit of 12 dB if you can read it, 12 dB of noise suppression. What happens with noise suppression or any of those schemes is that they introduce their own distortion, right? And that distortion can be in the form of sort of singing, it sort of puts a musical tone onto the voice, or other distortions which automatic speech recognition engines just do not like, okay? So that's all well and good. We had some babble noise from the New York Stock Exchange because New York Stock Exchange at that time was thinking about using automatic speech recognition on the floor. If you've ever been on the stock exchange floor, you'll know that that's one of the noisiest places that I've been, except Formula One race cars, but that's another story. Now, if we now replace the car noise with Babel noise, okay, that was recorded on the stock exchange floor, now you begin to see things that you kind of believe, you know, that the microphone is, you know, is doing what it should be doing. So there's some mystery there. I think I know some of the answers, but I don't know all. And one of the things that we may do in the future is to begin to reopen that here and try to see if we cannot really pin this down. On the car we had gone to, just before I left Bell Labs, we were taking data, and I believe that data is available in a car with various directional microphones, and in an effort to prove or disprove the Keduncan experiment. Okay? What I'm going to do now is talk about microphones that combine both higher directivity and signal processing. In many cases, the exact location of the noise source that you want to get rid of is either not known or is discretely placed. And one of the things that always happens earlier in teleconferencing is that you have a view graph machine or something on the table with a motor running. And of course, you put the microphone right near that source, and you get havoc on the other end. And Gary Elko, and I promise you that I won't show you very much more math, came up with a very interesting scheme in which he has two pressure microphones that are summed over two different loops with some delay in both loops. Don't worry about this. These are just the pressure from the two microphones separated by some small distance. What is important here is that if you normalize the outputs of those two microphones in the arrangement that's here, only one parameter, just a simple gain factor, is all you need in order to place a zero or a null in the backplane of the microphone. Any of these characteristics, you see there are nulls, except in the very back here, that are at least 15 or 20 dB down from the front, right? And what this means that this microphone is now, let's say, smart in the sense that, that it can aim a null wherever you want it in the back plane. Come on. No, it's not coming up. I just had it up. Oh, here it is. Okay. This is pretty self-explanatory.
We would like to demonstrate a new adaptive microphone that selectively adjusts its directivity to minimize noise signals that arise from the rear of the microphone. The system is composed of two omnidirectional microphone elements, which can be seen in the array that I'm holding, a forward element and a rear element. By combining the two elements in the signal processing algorithm, we can form the best directional pattern which fulfills specific constraints that require the microphone to be unidirectionally sensitive. As a final demonstration, I will talk from the front of the microphone with an interfering noise source in the rear. Initially, the pattern is set so the microphone is equally sensitive to front and back arriving signals. This is the interfering noise source, which we'll now turn on. It may be difficult to hear what I'm saying since the noise source is so loud, so we'll now push the adaptive microphone. I think you can hear a decided advantage of using an adaptive microphone in this situation. I can even rotate the microphone and still realize the same advantage.
Okay, so you see the thing is smart enough to know where the noise source is and keep the null in that plane as he turned the microphone. Okay. Now, okay, I did the smart microphone demo. Sorry for being a little behind on this. Okay, so now we've taken care of first order, right? And we've gotten what we can there. So the next logical thing is, well, let's go to higher order, right? And so our next step was to go to second order, right? And this is essentially just doing 2 of what we had done in order to get a first order directional microphone. And for the delay tau equals 0, what we get is again a figure of 8, but now the directivity index has gone up to 7 dB. So this is a very nice gain. We make the delay right, and we get a very nice second order unidirectional microphone. Now, okay, so you look at this and say, okay, great. Why not third, fourth, fifth order? Because now you can get this thing down to a pencil beam. But there's one thing that gets you, and what prevents that is that the response of the microphone goes with omega to the n. Okay, so for a first order unidirectional microphone, the response rises with omega, which is 6 dB per octave. For second order, 12 dB per octave, and so on, right? Much more than 12 dB per octave to correct for is a problem. Because what you do when you lift that up to get a flat frequency response, you also lift the noise of the microphone, right? And that shot noise, front end transistor noise, and thermal noise. And this, we're right on the, almost on the ragged edge with second order, and you go to third order, you're kind of really in trouble. Now what I've shown here is that you can do this with 4 microphones. Can you reduce the number of sensors? And the answer is yes. You use figure of 8 microphone. This is just a pressure microphone that has both the front port and rear port open, right? And so now you can reduce it to 2 sensors. Okay, and we have this D2 here, and that's path length around the device. And the reason that we're doing that is to increase the sensitivity, right? Because you remember for a dipole, it's the separation that gives you the signal. And of course, the closer those microphones are, the smaller the difference. And so what we did was to increase that difference by providing a baffle so that the sound has to travel around that baffle to get to the back port. And this gave us the gain that we needed in order to make a second order. Now there's one other interesting thing here. Notice that the phase of these microphones is plus, minus, minus, plus. I looked at this one day and I said, that's kind of interesting. When I look in the mirror, this is precisely what I see. Okay, I see, and when you look in a mirror, that's what a mirror does. And it turns out that if I take a single unit, a single first order differential gradient microphone, and place it next to an acoustic reflecting plane, you get a second order. So it's possible to go from the 4 sensors down to even 1 sensor and get the same characteristic. And what are those characteristics? Here they are. I'm sorry for the size here. But this is from 500 hertz to 2 kilohertz along with the theoretical analysis. So you see, this is very, very interesting results, and that we get a great comparison with what is expected from technology. Now, one other application is going back to the handset, okay, and especially if you want to do speech recognition and you don't have ideal conditions. Ideal conditions meaning that you don't have the 15 dB signal to noise ratio. What can you do here? I got involved in this through a very, very interesting way. The Air Traffic Control Center in Aurora, Illinois, had a great problem in being able to communicate with the pilots. And the major reason was they had a huge low frequency noise in the room that was due to the cooling of the computers and of the operators, right? And so we were asked to see if there was anything that could be done to help them out. And when I looked at what they were using boom microphone, but they were using omnidirectional microphones. And so it was very easy. I said, use directional microphones, use a close talking microphone, noise canceling microphone. And so he asked me one simple question. He says, how would you like to be in an airplane when the operator kicks his microphone up to take a sip of coffee and tells you to come in on, I've forgotten, those things that get confusing because of the lack of the right frequency response, right? When he kicks that microphone up and away from his mouth, he's increased the distance and he's not in the direct stream. So would you like to be on an airplane when he does that? And he says, come in on runway M, and you hear something, and the pilot hears something else. And I said, no, I really don't want to do that. But this also stimulated us to think about how we can do this. If you take two microphones, two first order gradient microphones, and space them some distance apart, right? And now I put them right up at my lips. And remember, the sound field is not plane at that point. It's a spherical sound field because it hasn't traveled far enough to become a plane wave, right? And so this means that even in those small distances, that smaller distance, there's enough difference between what's picked up by the first microphone and second microphone to actually generate a lookup table that will tell how far that microphone is away from the source, within limits. I mean, once you get out a certain distance, that all fades away. And so the next demo that I'm going to show you is a demo of the adaptive microphone. You can tell how long ago this is. How come? Oh, that should stay there. But I've got to get it down so I can get this other one up.
Okay, as you see, if I talk very close to this microphone, everything sounds all right. But now if I move it away from my lips, you'll notice that not only does the amplitude decrease, but the frequency characteristics are degraded tremendously. As I talk to it and move the microphone away from my mouth, you'll notice that both the amplitude and the frequency characteristics remain reasonably constant over the distance. I can move it away and slightly down, and it does not change, or slightly up, and it does not change that drastically.
So you see, with that correction in there, you can get this microphone to have a reasonably constant response over the range that we're interested in, and or at least I think that this can be a great help in speech recognition in a noisy environment, because the recognizer gets used to a certain spectrum and a certain level, and if that changes, it's going to reduce your accuracy. And so the combination of a second order microphone, which will very definitely improve the signal to noise ratio, and now if you make it adaptive, right, you've essentially solved both problems. The next step up the chain is to go to arrays, and this is where you have a bunch of microphones in a linear array, and there's some applying some delay, which will change the direction of the main beam. And what we've done is to, sorry again for this, I have to redo this view graph. This is the array here. There are about 30 microphones here. Now, remember that linear arrays are dispersive systems. By dispersive systems, I mean that their directivity is a function of the length of the array, right? And so for very low frequencies, you need something about as tall as I am. And for high frequencies, you can use an array that's very short, right? Now, also important in these arrays is the spacing between sensors, because the space between systems will give you the will alias. In other words, you get not aliasing is not the right word. You get poles and zeros in the response that are a function of the length, right? So we took a trick from loudspeakers where they give you a subwoofer, a woofer, a tweeter, and a mid-range. And so if you can see these dots, here's the short array, right? And then you see that there are about 3 spacings here as this gets longer and longer. And this is what we call a harmonically nested array, right? And what this does is that it gives you a beam width along the length of the array of about 20 degrees, okay? Now, again, making these sensors first order and placing them on a wall with the small spacing, you get the mirror image. And so now what you get in this direction is a cosine square pattern. So now you can get an extremely directional microphone which has its own hazards. And the hazards of directional microphones is that they have to point at the source that you wish to pick up. Otherwise, it's junk, right? And so, these are patterns that measured patterns. You'll notice that at some frequencies you do get some side lobes that are above what is predicted from the theory. But now, going back to the first picture I showed you, applying the right delay so that these microphones look as though you have turned them in a certain direction for the plane wave. And what you've really done is just applied delay down the chain of microphones so that they sum for a wave coming in from a different angle. And you see we can get many different angles by steering the microphone. When you get way off to steep angles, you do get a few problems, but we think we know why that's there, and that's mainly because of the phase difference between the individual elements along that array. Because you see, when you begin to sum a whole bunch of microphones, the magnitude of the microphones are important, but also the phase characteristics of the sensors are equally important. One of the first applications of these arrays happened in Disney World's Alice in Wonderland. They had created kiosks when you come out of one of the buildings. I think it was the main pavilion, and Alice has lost something, right? And so the idea is that the audience interacts with the visuals to tell Alice where to find, or the rabbit, I've forgotten. I couldn't sit through that whole thing, to find this device. And what Disney was using were $40 microphones on a cable, and they were passing this to the, I know, so you pass it to the kid who knows, and he says, look under the rock, right? Well, they were losing money on that because microphones would disappear almost as, as one group came out. And so they were thinking about discontinuing that exhibit. And so one of the things that we did in the kiosk was put the array that I just described up in the ceiling. And this is a pretty high ceiling. This is about a 8 or 10 foot ceiling, right? And we arranged the beam so it covered the entire sofa, right? And that's using the second order in the direction where you got enough coverage for the whole thing. And it works still works today beautifully, right? And its first application of, that we know of speech recognition in a quasi-public environment. Of course, you must understand there are only a very few words that this recognizer would, it's not like what you guys are interested in, and that is, having an infinite vocabulary. And the next step, of course, is that we have a one-dimensional array. What about a two-dimensional array, right? And so this array is again harmonically nested, 1, 2, 3 octave nested array. I think about 400 microphones in this array. And we took this array and placed it in Ondel Auditorium. If the lights, I don't know whether the lights can go down because I do want to show you this. Yeah, try that. This is a 400-seat auditorium, okay? I don't know whether you can see it or not, but here's the array in the ceiling here. Now, Ondel Auditorium, well, first of all, Murray Hill was what was known as Mecca. That's where most of the principal investigators and research were located. And so many research colloquia originated from this location. But we also had research people and many other people who were interested in these colloquia. And they were distributed in many places, right? And one of the major problems, and I'm sure that's happened to you, especially if your lecture is being simulcast or telecast, is please repeat any questions from the audience, because the far end is left out. If I don't repeat the question, you don't know it. If a question comes in from the far end, you know the question because that's broadcast in the audience. And so what we did with this microphone was, and here are the directional characteristics of the microphone. This is just symmetrical with a beam width of about 20 degrees. What we do with that is we generate 2 beams, okay? One beam continually scans the audience. I mean, it's a very fast scan, and what it's looking for is a talker. And the minute a talker appears, this beam here gets steered to them. And this all happens in about 15 milliseconds. You kind of lose the first part of it, but you quickly catch up. And this is, each one of these contours is 1 dB. And this is the whole audience area in Ondel Auditorium. And you see we cover very, very well the whole audience. In fact, it was kind of fun to sit back and eavesdrop on conversations that were going on in the hall. We had to warn people because of that. We also, it's another kind of interesting phenomenon, and that says, wow, this is really neat. Why don't we, because in a lot of cases you can't, the rest of the audience can't hear the question. So why don't we play the output of this microphone through the PA system, and that everybody can hear the question. It didn't work. I guess you can figure that out too. It kind of dawned on us, after we tried it, because what happens is that the loudspeakers are usually louder than the talker. So what the microphone says, oh, there's the talker over there, and points to the loudspeaker, and then of course everything disappears. But, everything does not always work as you expect. Arrays, as I mentioned, are very interesting devices, but the shortcut, drawbacks of arrays are twofold. One, they are dispersive, and 2, they have to be very large. Okay. If you want to go down to cover the full voice range, you need something that's about 6 feet long, right? And so this means that you've got to come in and you've got to put these things in the right place, and they require steering. I'm not saying that they will not and cannot be used. I'm just pointing out some of the drawbacks. And so one of my colleagues' students, Jens Meyer at the University of Darmstadt, came up with a very unique idea. And that is building what is called an Eigenmic. And it gets its name because of the way the signal is processed. You have, I think on that sphere, it's about 24 pressure microphones that are mounted on a rigid sphere. And what you want to do is to decompose the incident pressure into spatial harmonics. And this is where it gets its name in terms of a standard Eigen microphone. And what happens here is that you can get up to third order directional beams through in any direction through the axis of that sphere. The sphere is about 3.75 centimeters in diameter, 24 elements, and you can get up to third order, which gives you roughly 30 dB of rejection. 12 dB of directivity index and better. The colors here just shows the array sensitivity for a certain setup, and in this case it forms a dipole. The red is the hot spots and the blue is the cool spots. And here are third order beams. All of these are theoretical. And then here are the measurements of the array at 3 kilohertz. And so you see that, that we are doing pretty well here. And what we think can happen with this microphone, and we're going to find out around here pretty soon because I'm getting one of these microphones for experimental purposes. One ought to be able to come and drop that microphone down, at a convenient level from the ceiling, right? And now anyone who speaks in the audience, all you need is an algorithm to say, okay, there's speech coming from over here, and now you can get the response. It's also very interesting, and one of the things that we want to do is to see if we can apply this microphone to the evaluation of rooms. Very frequently you're concerned with a specific echo that's coming back and slapping off of a wall. And so one might be able to hang this microphone in the Eigenmic, say in this room, and resolve the direction of all of the reflections that are coming from anywhere on the wall, which will make it an extremely interesting analytical tool. It's also one of the, I love Discovery because of the tremendous visuals that you get, where you can count the whiskers on a big cat. But you can't hear that cat in a way that you would like. And I think the Eigenmic would be a very interesting tool to plant wherever that guy is going to be, and now you get all of the sounds around. And by the way, you don't have to do this on the spot. You can record all 24 microphones, and then at some later date, form your beams in the direction that you want to go. So it's kind of like photography in the way that you take a whole bunch of pictures and then you narrow it down to what is desirable. I mentioned earlier and showed you the picture of the Internet Protocol telephone. And the reason I want to talk a little bit about this is because I think that this will be interesting to you and in the future also. Telephony and more particular conference telephony has been really limited by a number of effects. One, it's generally not truly full duplex, okay? If you try to cut somebody off as you do in a normal conversation, you kind of step on them and the thing does its own thing and you don't get... and so the market didn't take off mainly because of, again, bandwidth restrictions. The interesting thing about the emergence of telephony over the internet is that you're no longer limited to 300 to 3,000 hertz. You have a very broad band of frequencies, and this is also interesting. The second thing is that in conference telephony now, what you have is one loudspeaker that sits out in the middle of a table somewhere, and this completely ignores one of the very excellent tools that the human being has. The human being has 2 ears. It's able to resolve in the spatial direction, and we depend on that. You know, in a real conference, when you're all sitting around a table, you get certain cues that you perhaps don't even realize. Even if you don't know the people, in 10 minutes, you've identified the quality of that person's voice. You know roughly the location, so you don't even have to look up. You know who's talking, and so you begin to prepare your answer for that. Now, you don't get any of that over telephony the way it is now. One other interesting aspect that you'll hear here, and that is the great improvement that you get with just a little bit more bandwidth, especially in communications. What I'm going to do is to play you a number of coders. First over telephone bandwidth, then we'll go to wideband, and you'll see where the cutoffs are.
The heart beats strongly and with firm strokes. The cruel was worn in a thin silver ring.
Is that loud enough? Everybody hear that? Okay, that's 2.4 kilobits. We go up
The
to...
heart beats strongly and with firm strokes. The cruel was worn in a thin silver ring.
So you see over the telephone bandwidth, even going from 2.4 to 8 kilobits, perceptually there's very little difference, right? And so what that's telling you is that it is really the telephone bandwidth that's causing distortion. Let's do it again.
Sunday is the best part of the week. The doctor cured him with these pills.
And now let's go to wideband, same code.
Sunday is the best part of the week. The doctor cured him with these pills.
Great improvement. We go out to 32 kilobits.
Kick off the new year with a gift from 800 Flowers. Just visit any 800 Flowers store during January's Winter White Sale, and you'll enjoy special savings on white. Kick off the new year with a gift from 800 Flowers. Just visit any 800 Flowers store during January's Winter White Sale, and you'll enjoy special savings on white.
So what this is really saying is that the transition is taking place right here. With 16 kilobits and broadband, right, you get a great improvement in the quality of the speech. And we think, too, that this will also help in speech recognition, because in many cases you want to either record record the output, and I know that there are some schemes that are talking about taking those recordings and now converting them into text. And we think that this will be greatly helpful here. Now, what about echo cancellation, right? That's an important point when you have people in one room that are talking to those in another location. This is only half of what's really needed. Whatever I show here, there has to be a duplicate on the other end. You have a talker in this room that speaks, and that is transmitted over to the next room, and of course, along with the transfer function of the room, gets picked up by that microphone, and of course you can have an open loop unless you do something about it. Well, an echo canceller, it just basically subtracts off any signal that's coming in this direction from any signal that's going out in the other direction, right? And of course you need another one in the other direction to do that. Now, it's kind of interesting when you try to apply stereo, you run into one great problem, and that is the talker is picked up by both microphones. You have two transfer functions, and they are both picked up by the same microphone. So now the echo cancel is confused. It doesn't know which to work on, you know. And so you get gobbledygook coming out of here. Jacob Benesti came up with a very interesting solution to this problem. And that is that he put some different nonlinear distortions into both microphone and into both channels, right? And now this allowed you to pull apart this and know which echo canceller should be active, and this is mainly due to this distortion. The distortion with speech is not recognizable. For music, it's a different story. We can't do music that way. And so what we're looking at here is that if you have two conference settings, what you want to do is to immerse, in a virtual sense, these people into the environment that exists here. And of course, you are not limited. If you can do it for 2 channels, you can do it for 4 channels or 5 channels. And so the future, we think, will look something like this, where you will get the ambiance of the room from which you're coming. I don't have that stereo demonstration. I couldn't get that to work. And that ends my talk, ladies and gentlemen. Thank you very much. Okay, wake up. Any questions?
So just going back to that slide you showed near the beginning, the performance of the directional microphone versus the omnidirectional microphone in the presence of noise. Just wondering how that compares to human performance if we cover 1 ear, which presumably gives us an omnidirectional, the equivalent of an omnidirectional microphone.
I'm sorry, would you repeat that?
So the question is, how does human performance degrade when we cover 1 of our ears?
Oh, tremendously. And if you don't believe it, well, so, there are a number of other major features in going to stereo. And one is the cocktail party effect, okay? And that is, if you're in a positive signal to noise situation, and there's even distance between you and the person that you're communicating with, you can still communicate, right? And people think it's lip reading, and there may be some of that. But it is really the fact that you have 2 ears, right? And the combination of those 2 ears gives you the ability to do some spatial, to spatially resolve the signal that you're interested in. Next time you're in an environment like that, just stick your finger in 1 ear. And what happens is that everything turns to unintelligible babble, even the person that's right next to you. So the human being is really uniquely equipped in that it has 2 very good receivers and a tremendous processor sitting in between that's doing things that we still don't fully understand.
Are there any curves in psychoacoustics which show performance degrading or something? Yeah,
there are. I haven't looked at those in a long time, and I can't tell you where that falls off. But I have seen those results. Yeah. Well, thank you very much.
I have another question. In these football games, I've seen these people carrying these parabolic plastic dishes with a microphone inside. And how do they compare? What kind of gain do you get with that?
Well, there are, if you notice, the sound is not very realistic, okay? And one of the reasons here, again, is that the dimension of the dish has to be comparable to the wavelength. And these things are much smaller than the frequency range of what's going on in the field, these guys clashing into each other and so forth. The focus of a dish can be very sharp, right? But again, you run into the problem of getting that thing right at the source. And you see these mechanical systems in that somebody's sitting there holding it, trying to aim it. And they even have a gun sight on the thing to try.
Sometimes even have that.
Oh yeah, they do both. They listen and they also use a gun sight to zero them in. It's very interesting technology, but I think rather limited in a sense in the same way that linear arrays are. And that's the reason that I think, personally, that differential systems are far more interesting. And we'll see pretty soon if they are also more usable in multiple spaces, or in spaces where there are many people trying to get a word in. Yes?
I have a question about the experiment you did when you actually added speech with noise, like this, and you were measuring accuracy. And I used to think that people sort of change the articulation of their speech when they're in a noisy environment. So results you get by artificially overlapping noise with regular speech are sometimes distorted. Is that true?
It is. And that's one, that was the reason that we wanted to go to a live car and take the recordings of the speech in a car. And that's, I think it's the Lombard effect is what it's called, right? We do exactly that. As a matter of fact, there's a very interesting article in the New York Times yesterday about rage in using cell phones on trains. And I certainly admit that it's very noisy. I mean, very annoying. And the reason that it's annoying is that people shout into those telephones. And why do they shout into the telephone? Because they're picking up noise, and they haven't designed the cell phone correctly. Okay, because the other thing that determines how loud you talk on the phone is a side tone. And that's used in telephony, side tone. In other words, they take a part of your voice and feed it back through the receiver so that you can hear yourself. And so you talk at a level, you tend to modulate your level by what you're hearing coming through the telephone. And of course, the ambient noise and the fact that the side tone is not set right to compensate for that is a problem. There's a great solution for that. All you have to do is use the adaptive close talking microphone, and then tie measure the signal to noise, and then give the user the right side tone, and he should modulate the level of his voice to be more reasonable in a noisy environment. Conjecture now. Thank you.